Hello everyone. In this video, we are going to talk about one of the most important tasks in robotics called forward kinematics. If you remember from our previous videos, I mentioned that there are two um, spaces we can relate to the robot. One of them is called the joint space or Q space, which involves the joint variables. So let's say if you look at this 6 degree of freedom robot, correct? So here you see a cylindrical robot with a spherical wrist. And you see it has 6 variables, theta 1, d2, d3, theta 4, 5, and 6. Correct? So these are the variables using which I can form the joint space. Okay, so let me write it down. Theta 1, d2, d3, theta 4, and 5, and 6. So if I give you these right now and say, hey, I know exactly how each one of the joints in the robot move, how much. And I also give you the geometry of the robot, which is the length of these links, okay? So this link here from the origin of the first coordinate to the next one, the next one, the next one. So I give you the geometry of the robot. And then I ask you, okay, now look at the end effector here. And could you tell me where the end effector is and what is the orientation of the end effector? If you remember, we had the rigid body motion, and the rigid body motion could be described by a homogeneous transformation matrix H, which has a rotation matrix R in it and a translation vector D, correct? So here, if I call this basically coordinate frame that is attached to the end effector, xn, yn, and zn, and I call the coordinate frame attached to the base of the robot, x naught, y naught, z naught. If I ask you what is the translation vector from the origin of frame 0 to frame n, which is this vector here basically, which you might call d of n with respect to 0, and then what is the orientation of that frame with respect to this one. So what I ask you to give me is r of n with respect to 0 and d of n with respect to 0, correct? This task here is what we call the forward kinematics, okay? So forward kinematics means going from what? From the Q space of the robot to what? To the workspace, right? Remember, workspace is the part of the world that the robot can operate in, the points that the robot can touch, whether at arbitrary orientation, which we call it dexterous workspace, or it can just reach them at specific angles, but not arbitrary, which we call them just reachable workspace, correct? So these relations, these formulas that you need to develop to go from Q space to the workspace, we call it what? We call it forward kinematics. Or in brief, FK. So here is the Q space or the joint space. And here is the workspace. Good. So now these equations will be definitely nonlinear equations, and we'll see them. And for them, we definitely will use those homogeneous transformation matrices H, which involves the 4x4 matrices, if you remember. So this task is very important, as I said, for robots. And why is that? Well, the reason is if you want to perform any task, what is interacting with the environment is the end effector. But the positions are described with respect to the base, correct? So I know that, let's say this is the base, and I know that here there is this table, and there is this object here on the table, and I want this end effector to go and grab it for me. So I know the position of this point with respect to the base. I know this vector, okay, this R. I know that. Now I have to force the end effector vector d of n with respect to 0 to be kind of the same as this R, and then change the orientation of it so that, for example, if I want to grab it from the top, the end effector comes like this so that it can grab it, right? So I have to know that. Now that's the next task that we'll do in separate videos, that if I give you this position now, if I give you the orientation now that I need for pickup, now what angles, what distances, what prismatic joint variables I need to make it happen. That task is called inverse kinematics, which we'll do later, okay? So if I give you these, and then I ask you to go back and give me the joint variables, this task, we call it the inverse kinematics. And we'll talk about that in separate videos. And both of these tasks are super important, okay? Because this forward kinematics will tell me where I am at the moment, where is my end effector, and not only it only gives me end effector, it tells me more than end effector, because I know the total geometry of the robot. Not only it gives me the end effector position orientation, it gives me also the position of any other point on this robot. So if I consider any point on this robot, it can tell me where that point is right now. And why is that so important? Because if the robot is operating in an environment that is not perfectly controlled, and there are obstacles on the way as it tries to go from one point to the other, you have to avoid what? Yes, collision. Okay? You have to make sure that none of these points on your robot will be in the same point that the obstacles are, right? So that's one of the hardest tasks, is to avoid collisions and do what the task that we called in the earlier video path planning. Okay? So it's not just always the end effector that matters where it is and what orientation it has. You have to care sometimes about what? About the position of the rest of the points of the robot. Okay, these are important as well to avoid collision, because not always around the robot everything is clean and free. Sometimes many robots have to work in basically work synchronous together, right, at the same time, and they are close, and they when they fully extend, they might hit each other. So this forward kinematics allows us to avoid collision as well, know where we are every point on the robot, including the end effector. The equations are typically very nonlinear. We're going to see that. And there are so many different ways to calculate forward kinematics. We discuss in this video one of the most common methods of calculating the equations, which we call Denavit-Hartenberg convention, or DH convention. This is the name of the two people that made this convention. This is a very good systematic approach to calculate the R and the D. We'll talk about it. It is involved. It might in the beginning look a little bit harder than some other conventions, but it is very systematic, and not only it helps me with forward kinematics. Later I'll show you when we go to forward differential kinematics and want to calculate, well, angular velocities, linear velocities, calculate what we call later Jacobian matrix, this method can make life very easy back there. Okay, so we talk about it with several examples, and then there is a separate method we also gonna discuss, which is not as complicated as that. It is quite easy, but then you have to get involved into partial derivatives if later you want to calculate, as I said, the Jacobian matrix. So for forward kinematics, this method, which we call the vector addition method, is quite easier than the DH method. No discussion, no argument whatsoever, okay? It is easier, but as I said later, when we want to do a more advanced task, this is not going to be as systematic, and it is prone to more errors than the DH. But each one, as I said, each one of these two methods, vector addition or DH, they have their own advantages, okay? So we are going to look at DH in this video, and in the next video, we're going to talk about the vector addition, okay? Okay, what does the DH method say? So it has two major assumptions. First of all, that when you attach each coordinate frame to one of the links, the new x-axis, the x-axis of the new frame, is perpendicular to the z of the previous frame. For example, x of 2 is perpendicular to z of 1. X of 5 is perpendicular to z of 4. Where z's, as you know, and we discussed earlier, are the axes of actuation for each joint, okay? So whether it's rotary or prismatic, each joint has an actuation axis, and we call it z, right? And then we also have x and y for each coordinate frame. Now x is perpendicular to previous z. Also, it has to intersect it. Okay, it has to intersect it, so they cannot be skew axes, right? Z I minus 1 and xi cannot be skewed. They have to be on the same plane, intersecting each other and being perpendicular to each other. If these two assumptions are observed, then DH convention will guarantee you a proper unique solution to the forward kinematics problem. So how does it do that? Here I'm showing you two links, link I minus 1 and link I. And as I said, to each link we are going to rigidly attach a coordinate frame. So we attach coordinate frame I, xi, yi, zi, rigidly attach it to link I, and similarly attach xi minus 1, yi minus 1, and zi minus 1 attach rigidly to what? Link I minus 1. Now, when we say attach it rigidly, it doesn't necessarily mean that the origin of those coordinates are on the physical object. In this convention, there are cases that you see the origin of the frame is going to be outside the physical object, okay? What matters is here we assume that hypothetically this frame is attached to the, it's like welded. For example, here you see the OI is out of link I, but here we can assume that if we assume these axes are some physical objects, physical rods or whatever, we can assume that, for example, this rod of axis ZI is what? Is welded here, okay? So you have some welding here, and so the angle of it and the orientation of it, the position of it cannot change. So just keep that in mind. No need to be the origins to be on the parts. Good. So now the way you describe the position and orientation of frame I with respect to frame I minus 1 is determined by 4 parameters: AI, DI, alpha I, and theta I. Okay, each one of them has a name. We'll talk about it. Okay, so we have the length of the link AI, we have DI, okay, which is the offset. We have alpha I, which we call the twist angle, and we have theta I, which is the rotation angle. So there are 4 parameters. Now, let me describe them exactly, how we measure them and how we determine them. And then we talk about how to form the homogeneous transformation matrices that I told you earlier, and then how we go from the very first frame to the very last frame, okay? Okay, so here I added the names for you. As I said again, A is called the length of the link, D is called the offset of the link, alpha is called the twist angle, and theta is called the joint angle. So just wanted to know that we go from one origin to the next origin using 4 parameters, A, alpha, D, and theta. Now, what are they? The first two, if we want to describe, we can call them basically D and theta. So actually the first two are these two, really, D and theta. These are the first two that we use, and then followed by A and alpha. So D and theta, if you look at them, they are both along or about the axis zi minus 1. This is how we describe them. So how? First, let's look at the angle theta. How do we describe theta? So theta means if I want to go from origin OI minus 1 to OI, the first thing I need to do is to align my axis xi minus 1 with the axis xi. So first I align my x-axis of the previous frame to the x of the new frame. I align them together. How? I'm going to rotate my coordinate about zi minus 1 with angle theta I. Okay, so if I rotate, I have a rotation about zi minus 1 with angle theta I. If I do that rotation, then it will force my xi minus 1 to align with what? With x, correct? With xi. So that's the first thing. And since that is a rotation about the z-axis, so if I want to show that here, as you can see, I show it with the rotation z and angle theta. So here you can see this part of it is a rotation of z and angle theta. There is no translation here, right? So this first homogeneous matrix is going to represent that first action, rotation about zi minus 1 with angle theta to align the x's. Then when I align the x's, my next step is now I move from origin OI minus 1 to this intermediate point here. So if I move from the green point to the red point, then in which direction should I move? Well, clearly I should again move along what? Along zi minus 1. And how far should I move? I call that displacement what? Di, the offset. Okay? So if I move along the z by di, then I go from green point to what? To the intermediate red point. And that's what you can see here. It is a translation about z and di, which you can see here. And clearly there is no rotation, so it is an identity matrix. So far I align the x-axis, I move to the intermediate point. Now it is time to use the new x-axis, which, by the way, as you can see, the new x-axis, if you look at it, it is perpendicular to the old z-axis. You can see the angle here. And it is also what? Intersecting it. At which point? At this intermediate red point. So the two assumptions of the convention that xi is perpendicular to zi minus 1 and it is also intersecting it, you see both of them are observed here. Okay, fine. Now what do we do? The next thing we have to do is, of course, move from the red point to the blue point here. If I put a mark here, blue point, the origin of the frame I. Well, how can I go from red point to the blue point? It's quite easy, right? All I need is to move along the new x with this length of AI. And you clearly see that AI is the length of what? Link number I. And it is translation about which axis? It's about x-axis. So all I need to do is now to move along the x-axis with the distance AI, as you can clearly see, and no rotation. So now I'm completely gone from the green point to the blue point, and my x-axes are also aligned already. Now, when the two x-axes are aligned, does it mean both frames are perfectly aligned? No. If I want both frames to be perfectly aligned, at least I need two axes. At least I need two axes of the two frames to be aligned, then the third one will automatically be aligned because they are both right-handed systems. So the x's are already good. Now what I do is align the z-axis. So the zi minus 1, so this direction here is the same as what? Zi minus 1. I try to align it by zi, by the new z that I need. And for that, I rotate about the x-axis, the new x-axis, with this angle alpha, which we call it the twist angle. That will force the z's to be aligned too, and then since x's are aligned and z's are aligned, automatically the y's will be aligned as well. So the last rotation is alpha about the x-axis, no translation, and that's what you see here. There is no translation, but there is a rotation about x-axis with angle alpha. So the sequence of these four operations, rotation z, translation x, rotation x. The sequence of these four rotations will guarantee me going from origin OI minus 1 to origin OI and aligning what? The z-axis. So if I combine these four together by pre-multiplication, because each time I did it with respect to the current axis, if I combine them by multiplying them together, the resulting matrix will have a form like this, where all four parameters, theta, A, D, and alpha, you can see they are all shown here. And the result of that, I call it matrix AI. So what does matrix AI will give me? Matrix AI is a 4x4 matrix where the 3x3 portion of it will tell me how I go from what? From frame I to I minus 1 or vice versa. So it shows me the orientation of I with respect to what? I minus 1, and it shows me the origin of frame I with respect to I minus 1. Okay? So we call it AI, the I homogeneous transformation matrix. So this R of I minus 1 is this matrix. It tells me exactly how I go from one to the next orientation wise, and this guy is the D, which tells me how I go from one frame to the other translation wise. Okay, good. So everything is clear. Now, before I move any forward, I need to talk a little bit about the sign for the angles theta and alpha. So how do we determine whether alpha and theta are positive or negative? Because D and A are quite easy, right? D and A are quite easy. If I move along the positive Zi minus 1, Di is positive. If I move along the positive Xi, Ai is positive. That's not a big deal. But what about theta and alpha? So how do you determine the direction of theta? Well, theta has to align Xi minus 1 with what? With Xi. So that's how you determine the direction of what? Theta. Okay, that's how you determine the direction of theta. And now you look at the direction of theta against what? The direction of Zi minus 1. If theta is the same direction, if this rotation theta, for which you can determine the direction of it using the right-hand rule, correct? Is the direction of rotation of theta aligned with Zi minus 1 or is opposite to it? In this case, you see Z is upward. This theta looks like counterclockwise about it, so it is positive. But if I had to, for example, if Xi was here, so I had to go like this to align it. Now this theta I about that Z is going to be what? Negative. Okay, so that's how you determine whether theta is positive or negative, by aligning what? Zi minus 1, xi minus 1 to xi, okay? Whether the rotation that you need is about positive Zi minus 1 or negative Zi minus 1. The same thing for alpha. Alpha is about the new x, and it aligns the old z to what? To the new z. So now if you look at again this direction here with that x, that is a positive direction. Okay, but if zi is something like this, which means you have to rotate backwards like that, now this rotation about that x-axis is going to be negative. Okay, so I mentioned that as well for you here. Rotation about x to align zi minus 1 to zi. That's what determines whether alpha I or theta I is positive or negative. And we're going to work through a bunch of examples to exactly clarify for you how to determine what these signs. But just wanted to make sure we understand it. Good. So now I got my homogeneous matrix, which takes me from one frame to the next, I minus 1 to I, or I back to I minus 1. Good. So now, how can I go from the base of the robot to the end effector? Well, that's not so hard. Why? Because the first A matrix will take me from frame 0 to frame 1. The next one takes me from frame 1 to frame 2. The next one takes me from 2 to 3, and so on. So if I have this sequence of these A matrices from the first A all the way to last A, and I pre-multiply them, it can take me directly from base to what? To the end effector. And that is exactly what you can see here. That if I want h of n with respect to 0, which is telling me the rotation matrix of n with respect to 0 and the origin of n with respect to 0. So here, by the way, this d or o that you see, this o, is the same as d. Okay, so if we want to avoid confusion, maybe here I use the d vector instead of o, the displacement vector. Okay, so maybe we use it as d. That's okay, that's just the same thing. So as you can see, what is being done here is the first rotation matrix is multiplied by the second one, by the third one, all the way to what? The last one. Correct? So I'm multiplying A1 by A2 by A3 all the way to AN, and that will give me the overall what? The overall rotation matrix that I need to go from end effector to base, and from the translation that I need to make it happen. And here I also define another matrix. We call it the T matrix. The T matrix here, which describes the position and orientation of frame J with respect to frame I, is determined by what? By multiplying the A matrices in between them. Okay, so T here is determining the position and orientation of one frame with respect to other, and it doesn't need the two of them to be the end effector and the base. It could be any with respect to any else. Like, for example, I want to know if I have some coordinate frame here. Let's say if I have some coordinate frame here, what is the position and orientation of that frame, whatever it is, let's say frame 5 or frame 4, with respect to maybe this frame? Okay, now most of the time this is not super meaningful. What you really most of the time use is each one of those individual frames with respect to the base is what you most of the time use. And you might say, well, why should we even calculate that? What's the point? What we really need is end effector. We need to know where end effector is because it interacts with the environment. True, but remember, I told you one thing earlier about the importance of the forward kinematics. I said that it is not only to interact and do the job, but also to avoid what? Collisions. So if I want to know what is each point on this link, I need to know the rotation matrix and position of the origin of that frame 5 with respect to 0, so that I can calculate the location of the points on that link number 5. Okay, so we can use T for other frames as well as the end effector to determine their location and make sure those locations will not coincide with the location of obstacles in the environment. So those are good for collision calculations. Okay, but mostly what we really use these A matrices, we use them from the very first one all the way to last one, and we get the end effector position and orientation. Now, one important thing about these A matrices. In a robot where the joints are like prismatic or rotary, you can show that out of these 4 parameters, A, alpha, D, and theta, in each transition from one frame to another, only one of these guys is variable. The 3 others are just constant numbers. Okay, the 3 others are constant numbers. So for example, when I calculate the first A matrix, you see the A matrices, they are starting from A1 all the way to AN. So when I say A1, what does it mean? It means if I have a frame here attached to the first object, correct? So let's say I call this guy X1, Y1, and Z1, right? So if you look here, when I go from frame 0 to frame 1 and I form matrix A1, this A1 has 4 parameters in it, correct? It has 4 parameters in it, dA, alpha, and theta. Which one of them is variable? The only variable is that joint variable. So the only variable in them is only theta 1, the twist, if there is any twist, which in this case there is not, if the offset is, which is basically this amount of offset from here to here, and if there is any joint link here, X, which A, which we use 0 really, then if I want to write it in this case, so it is going to be like that, and then L, and you have 0 and 0. Okay, so this is your D variable, this is your A variable, and this is your alpha variable. I'll show you. We're going to go through examples. This is definitely fixed. This is this fixed L from here to here. And those two are 0 and theta 1. The only thing variable here is this guy. The rest of them are constant. So I can say my matrix A1 is simply a function of what? Theta 1. Okay? Then when I have a frame here, let's say, so I have a frame here, let's say this is Z2, and then I have, for example, this is X2, and then you need Y2 like downward here, then I can show you when I want to go from frame 1 to frame 2, the A2 matrix is only a function of this variable. It's a function of A2. When I go from 2 to 3, the A3 is only a function of the joint variable D3. Then the next one is only theta 4, next one is theta 5, next one is theta 6. So out of the 4 parameters, each time when we go from one frame to the next, only one of them is variable. Which one? The one that matches the joint variable. If the joint is rotary, then it's going to be theta that is variable. If the joint is prismatic, then it is going to be D that is variable. In other words, A and alpha are always constant in this notation. A and alpha are absolutely constant. Between D and theta, one of them is variable in each matrix. Which one? Depends on the joint. Prismatic is D, rotary is theta. So this whole H matrix that you get, or the Rn0 and Dn0, are basically functions of what? Functions of this, in this case, let's say the 6 joint variables or the 4 joint variables, as many joint variables that you have. Okay, and these are exactly what we wanted, correct? We say these guys, these are n0 and dn0, these are functions of what? These 6 joint variables. So when we find them as functions of joint variables, our task is over, correct? So here, let's say I write it as this, correct? So Rn is a function of that, and then D also, and 0 is a function of those. Once we have these functions, it's over. Anytime I know my joint variables, I plug them in and I can get R and D, and that means I know my end effector position and orientation. So I got my forward kinematics equations. Okay, so now the important thing is setting up the frames properly. And I mentioned all of this implicitly during the video so far and in previous videos, but just re-emphasize everything. If you have a manipulator with n degrees of freedom or n links, you really need n plus 1 frames. From frame 0, which is attached to the ground, that's your inertial or base frame, all the way to frame n, which is attached to your end effector. Okay? Z's are the actuation axes. Zi is the actuation axis for joint I plus 1. Okay, let's first do this and then we'll talk about the base frame. So let's first go through this first thing. And for that, we're going to go through an example. We are going to work on the 2 degree of freedom planar arm. So the planar arm is basically with 2 degrees of freedom. Here you have your first member pinned down to the ground, and then the second member pinned down to the first member like this. And at the end of the second member, what you can have is an end effector. Let's say here a gripper. So now, if you see here, I have this guy, which is joint number 1. The joints are numbered from 1 to n, and this is joint number 2. This is link number 1. And this guy here, if I can write an angle on it, this is link number 2. Okay, so these are link 1, link 2, joint 1, and joint 2. Clearly, you see it has 2 degrees of freedom, this rotation and that rotation. Now, the frames, there will be 3 frames, not 2. Frame 0, frame 1, frame 2. Where frame 0 is attached to the ground, frame 1 is rigidly attached to link 1, frame 2 is rigidly attached to link 2. And since link 2 and end effector are the same object, it means it is also attached to the end effector. Okay, the first thing it says is determine the actuation axes. So here you have 2 joints, there are 2 actuation axes. First joint 1, then joint 2. So we have 2 Z's. What are they? Clearly, both of the rotations are happening about axes perpendicular to the plane. So here, if I show perpendicular to the plane toward me with a direction like this, and then for the other one, something similar like this, right? And let me try to make it as parallel as possible. Then what do we call these Z's? We are not going to call them Z1 and Z2. We are going to call them Z0 and Z1. As it says, Zi is the actuation for joint I plus 1, which you can see here. So for joint 1, the actuation axis is called Z0. For joint 2, it is called Z1. Where is Z2? We'll talk about it. But Here you only have 2 degrees of freedom, so Z2 really, unless you want to give an actuation for this end effector, right? And kind of saying it's like 3 degrees of freedom. That's a separate thing. So these rules that I'm saying, these rules here, and I'm observing, they are for all of the joints except for the end effector. So here I do not really care at the moment about how the end effector is actuated, and I do not count it as one of the degrees of freedom of the robot. So when we say robot, we set aside the end effector, because you can connect different end effectors to a robot, okay? What we do in forward kinematics, we always try to describe the position and orientation of actually a point on this end effector to what? Or a rigid connection here to the very last link to the base frame, okay? Because we can change our end effector. It doesn't mean if we change our end effector, our forward kinematics equations will be different. No. The forward kinematics are really depending on the robot itself. The end effector is an extra addition to the robot, and we want to set it up so that it does not affect our forward kinematics equations. So here Z0 and Z1, what is Z2? We'll talk about it for the moment. Let's just stick to these because we have 2 joints really. Now the next step says for the base frame, for frame 0, 0, 0, x0, y0, z0, the origin and the direction of x0 and y0 are just arbitrary. Origin O0 can be anywhere on Z0, and the direction of x0, y0 are chosen conveniently as long as they are a right-handed system. So basically here what I have is, well, I can select my origin to be anywhere along Z0. So it can be exactly at the joint point, or I can take it out of the plane and bring it out and put it somewhere with some offset from the plane. But there is no reason. If everything is on this plane, why should I take my origin out of the plane and put it there? Correct? Why should my reference be outside the plane that everything is happening? There is no reason for that. So I choose my origin of frame 0 to be exactly at this point. So I call it O0. And now, maybe I can write it better. O0. Now, what about x0 and y0? Which direction? Well, it doesn't matter. All that matters is it's a right-handed system. So, for example, I can choose my, let's say, x0 to be something like this, and then y0 to be perpendicular to that. Let's say here, something like that. Right? Does it give me anything special? No. Here the x0 is just rotated with respect to the horizontal axis here, and y0 is also has to rotate the same angle to keep the system right-handed. So you see, although I can do it like this, but it doesn't give me any advantage over if I did x0 just horizontally to the right, and then y0 is vertically upward. That's quite easier to deal with because I can easily measure the angle of this link 1 with respect to it and call it theta 1. And if I rotate them like the previous case, then now I have to add or subtract this theta 1 from that rotation angle, which just makes my life a little bit harder. Okay, so this clear selection of x0 and y0 is very convenient. The system is right-handed, so I'm set about the first frame. And by first, I mean frame 0 base. Now, you saw that my original x0 was arbitrarily chosen. But from this point on, it's not the case anymore. Each new x, if you remember the assumptions of dh, each new x has to be perpendicular to the old z and also intersect in it. So when I come here and I want to select my x number 1, x number 1 cannot be free to choose. For example, you might say, well, can I also choose x1 like the previous case to be horizontally to the right? The answer is no, not in this case. Why? Because if you look, this x1 has to be perpendicular to previous z naught. Well, in this case they are, because x is in the plane, z is out of the plane, normal to the plane. So of course they are perpendicular, but do they also intersect? The answer is no. Your x is like here and your z is like there, out of the plane. Okay, there is no intersection here. We call these the directions, we call them the skew directions, a skew axis, right? Skew means the two vectors can never be put on the same plane, never can be considered coplanar, right? So because there is no intersection here, I cannot choose x1 the way it is right now. There is only one selection for x1. What is that? It has to be collinear with link number 1. If I choose my x1 to be collinear with link number 1, then when you extend it, it will intersect z0. Because you know, x1 and z0 are just really some directions, and they can extend both ways. So that's the only solution I have for x1. And since that is the case, automatically it means y1 should also be what? Perpendicular to x1 and z1 in a right-handed manner. So you see now x1 is forcibly determined through the two assumptions of the dh. Good, and then y is set and my frame 1 is set. Good, now let's go to frame number 2. Because remember, I said if you have 2 links, or n links in general, you have n plus 1 frames. So we also need a frame number 2, which is now attached to this end effector. Now, how do you set up the end effector frame? Well, in many textbooks, the method they suggest for the gripper is called the ASN or NSA, whatever you want to call it. And they say if it's a gripper like this, then the direction of approach of the gripper toward the object, this A, you can choose it to be your z-axis. The direction of opening and closing the gripper, you can choose it to be y-axis. So let's say in this case, for example, I choose the y-axis to be like that. This is called the slip direction, and you choose it to be yn. So again, S means slip, A means approach, and N here means normal to both slip and approach, which in this case, what should it be? Well, it has to be in a way out or in the plane that it's a right-handed system. Clearly, in this case, has to be out of the plane. We call it the normal direction, or xn. So if I want to follow the same method of ASN for the gripper end effector here, what happens? What happens is your x here is going to be out of the plane. Okay, your x is going to be something like z1. So this is going to be your like x number 2. And now, does that violate your DH convention? Yes. Why? Because x2 and z1 clearly are not perpendicular, they are parallel, and of course they will never be intersecting. So you see, that will clearly violate the I would say the DH, the two DH conventions. So although this is a common convention, but I cannot exactly use it this way. So if I want to use it, instead of setting my A to be the z-axis, I have to change it. And I have to choose my A to be the x-axis, actually. Because that's the only solution here you can have to keep the DH convention working, the assumptions not violated. Because remember, my x2 has to be perpendicular to z1. z1 is out of the plane, so my x2 has to be in the plane for sure. And then it has to intersect z1. And the only way that it can intersect z1 is, again, what? It is along the direction of link number 2. So that's the only solution here. So that when you extend it, it intersects z1. So in our case, we have to say the approach direction to be x number n. Okay? And then, for example, if now you say the slip direction is the y direction, keep it, then the normal direction can be, in this case, the z direction, and of course you have to make it backwards, which is in the plane, like this. So you can say this n direction normal is now z number n. Okay, then it would work. Yes, so that is x number 2 here. Then y number 2, you can select it to be this way, or if you want to keep constant or consistent notations, you might select y2 to actually be in this direction. Who said that y2 is just the direction of opening and closing? You might select it this direction. That makes your life easier in this case, because you see it's like y0 is direct and rotated by angle theta 1 to get y1. y1 is going to be rotated by this angle, which is theta 2, to get y2, and this is a very simple setting up of the axis. So what I will do here is I choose the direction of a slip, still in the direction of opening and closing the grouper, but to the left, positive. So slip, I say this is yn, and that forces my zn to be out of the board like this. So you see, I cannot exactly follow the approach to be z and the normal to be x. I have to reverse it. The other thing is, here we really do not follow the fact that z is the actuation. Because as I said, these rules that I say z are the actuations for the joints, they're all for the robots themselves, not for the end effector. The end effector is not a part of the robot all the time, because one end effector can go, another end effector can come. And it doesn't mean by changing end effector, I'm going to redo all of my forward kinematics. Absolutely not. Okay? So setting up the axis for the end effector not generally follows everything about the rest of them, but I would rather always follow the two assumptions of the DH, so that I can use the DH table completely. And what is DH table, I'll tell you. But I would suggest we do the approach direction to be x, the slip direction to be y, and the normal direction to be z in this case. So z, the last z, has to be what? It has to be out of the plane again, like this. Okay, so now I have set up all of my frames, correct? All the 3 frames that I need. And this is basically the summary of everything you see in this slide. Now here in these items 3, 4, 5, it is just trying to give you some suggestions for how to make these 2 assumptions work. Okay, so they are not something new, they're all related to keeping these 2 assumptions valid. What is that? It says there are several scenarios that can happen between the subsequent z's. Either the subsequent z's intersect, or the subsequent z's are what? Parallel, or the subsequent z's could be skew. Okay, so there are 3 scenarios between each 2 subsequent z's. So let's say z1 and z2. So either they are parallel, like this. It says if they are parallel, then there is no intersection point between them. Then choose your origin of frame 2 anywhere convenient, right? So it says choose origin OI what? If they are parallel, choose it convenient allying what? ZI. So anywhere allying the Z2, you can choose to be what? Origin of frame 2. If they are intersecting, then the life is easy. You choose origin 2 to be at the intersection of the two. And as I said, there could be a case of skew, which you cannot see it exactly here in terms. I can add it, but that's where here it talks about the common normal to them. Okay, so if they are skew, which means they are not on the same plane, so let's say here, for example, Z1 is out of the plane like this, and Z2 is in the plane like that, then there is a location for the two skew directions that you have what? The minimal distance between them, like this. This is the location of the minimal distance. Then this intersection of this minimal distance with Z2, you can call it what? O2, okay? There is one place that you can draw a common normal to both. That's the only common normal that you can draw to both of these lines. And that's where the minimum distance is happening. Then the intersection of that common normal with Z2 is going to be O2, okay? So if you want, here I can add it as some words for you. Okay, so here I added that wording for you. If they are skew, then there is a common normal to both, the location of the minimal distance, the intersection of which with ZI will be OI. So there are, as I said, 3 scenarios that can happen: parallel, intersecting, and skew. And we're going to see all of that in the examples we are going to solve. For the case of this 2D planar arm, you see that all of the Z's, Z0, Z1, and sorry, this is Z2. I don't know where Z3 came in. This is Z2. All of these Z's are parallel, okay? So I can choose a convenient location, but there are scenarios that they can be skew or they can be intersecting. Like, for example, for a spherical wrist, I can show you that, for example, in this case here, if you look, this Z1 and this Z2 are intersecting. So the location of intersection is O2. And I should be able to, if I look into some cases that I can find for you, skew cases as well. I don't see anything here, but I'm sure if I look into my examples here and there, I can find it. But skew, clearly you can see it here if you want. This is the case of the skew between the two axes. Now here, something like, for example, let me see if I can show it to you here. Of course, the Z's are here, not really, they are askew. Yes, they are. You can say that because if you look at the ZI minus 1 and ZI, their directions are different and their orientations are different. So if I do a little bit of cleaning here, so you can see a little bit better, you clearly can see that there is a common normal between ZI minus 1 and ZI, which is this guy here with length AI. And the intersection of this common normal between ZI minus 1 and ZI is what? 0.0I. So this general case that I showed here, it's showing a skew scenario. Okay? So that's all this item number 3 is trying to say, how to locate the origin of the new frame. And of course, then set X such that it is intersecting the previous Z and what? Perpendicular to it, and then Y will automatically be determined from the assumption of right-handed system. Okay? So let's now put that in practice in a few examples. Let's set up the frames for different examples and we practice how to set up the edge frames. Once we know that, then life is going to be a lot better, because robotics, like any other course, it is all about practicing, okay? So if I don't practice enough and I don't solve enough of problems, I can never claim to be understanding robotic very well. Okay, no, this is not going to be happy. So I'm just going to clean it like this. Okay, so these are the frames that I set up for the 2 degree of freedom planar arm. Now, let's look at some more complicated examples. So theta 1 and theta 2, you clearly see the 3 frames again. Now, we can, for example, look at the Scara example, right? This is the Scara. And here the axes are set up already, but if you want, we can practice together and get rid of these axes. So, or I can even show it to you on a picture if you want. If you don't want to show it on the schematics, then I can also show it to you on the picture. So, this is the schematic of Scara, as you can see, but again, I can bring the robot itself and I can show you on the robot itself how to set up the frames, but it's good to just see how to draw the schematics a little bit too. So here you have this first rotary joint, the second rotary joint, now the prismatic, and the way I put this plane, the direction between these two planes tell me the direction of what? The direction of prismatic motion, which is up and down here. And finally, I have my final rotary joint here, which is another Z. And then attached to that, I can have my end effector in any direction that I want. Okay, so this is my Scara with the end effector. There are 4 joint variables. And now I can get rid of this, okay? So we can practice the Scara together. Okay, step number 1, determine the z-axis, the axis of actuation. What are they? Well, these 3 joints, rotary, they're all z-axes. Their z-axes are all in the plane, upward or downward. So I can say, for example, I can set this guy up to be like my z naught, and then this guy, I can say this is z1. Then this guy goes up and down, so I can select this z to be either up or down. Now, most of the time this guy goes down then up, but it's up to me here how I would select the positive or negative direction of z2. It has to be vertical, but which direction is positive, it is absolutely up to me. So here, let's say, for example, I choose this guy to be downward. And then this guy also is going to rotate about this vertical axis. And again, it is up to me how to set it up here. And so here I set it up like this. The same as Z3. So these are my Z's, right? The actuation axes. Now, the next step is to go and set up what? My base frame. The origin of the base frame can be anywhere along Z0. It is completely up to me where to set it. And then X0 and Y0 are again arbitrary. I can choose them because there is no limitation on the first frame. X0 does not need to be perpendicular to the previous Z, which is Z minus 1, or intersecting it. So there is no Z minus 1. So X0 is free. And it's up to me how I want to set it. So here I go with setting up my x-axis to the right side like this, horizontal. And based on the right-hand rule, my y has to be in the plane. Okay, it has to be in the plane. And here I can show, for example, in the plane with something like this. So that is my origin O0, which is somewhere along Z0. Or that I choose the simplest scenario possible. So this is my base frame. Now let's go to frame number 1. If you see the Z's here are parallel, the two subsequent Z's are parallel. So O1, the origin of frame 1, can be chosen anywhere arbitrarily along this axis Z1. And X1 has to be perpendicular to Z0 and intersecting it. So since this Z0 is in the plane and upward or downward, X has to have one of the two directions. The new X has to be either similar to the previous X horizontally, or it has to be what? Out of the plane. Now the problem is, if it's out of the plane and somewhere along Z0, it's not going to intersect Z0, right? So if I select my, let's say I set my origin here because it's convenient, it's the most convenient. If I set my X1 to be like this, it's not going to work. Why? Although it is perpendicular to Z0 because it's out of the plane, Z0 is in the plane, but Z0 and X1 are now skew. They're not intersecting. So that's not going to happen. Okay? So the only solution I can have is to force X1 to be the same as X1 to be the same as X0. Now, when you continue X1, it is going to intersect Z0. Okay, and based on that, my Y1 is also forced to be in the plane. And this is going to be frame O1. Now, you might say you could choose a convenient location. What if you didn't choose origin O1 exactly here at the center? What would happen? Well, then what would happen is this. Instead of me choosing my origin there, then I can choose my origin to be, let's say, here, right? Then this is going to be X1 and this is going to be Y1. Still works because X1 is intersecting the continuation of that, the line of action of that will cut Z0 and perpendicular to that. So this is working, but that's not really convenient. It's offset from the center of the joint. Why should I choose that, right? So although I can select it to be with some extra offset like this, but I don't see any reason for it. Okay, so I would rather go back and choose my most convenient scenario, Y1 and X1. Now again, you go from Z2 to Z3, they are parallel. So again, the origin of that is Z2. I'm sorry, I don't know why I'm jumping a little bit. This is Z2 and Z3. And I can make my Z3 to be a little bit shorter than that. So I leave some room off for the end effector frame. So I can choose my Z3 to just be like this. Okay, so origin number 2 can be anywhere along this Z2, but let's look at X2 and see if we can find a convenient scenario. So X2 has to be perpendicular to Z1 and intersecting it. So again, since Z1 is upward, it has to be either horizontal or out of the plane. Again, if it's out of the plane, it's not going to cut Z1. So the only solution I have is for X2 to be horizontal. So I choose my X2 to be like this. That will cut Z1 perpendicular to it, and then based on this X and this Z, Y has to be out of the plane. So this is going to be Y2, and this is going to be origin number 2. Good, so I could set up my frame 2. Now I go to frame 3. Again, Z2 and Z3 are parallel, or in this case, collinear. And so I can select my origin 3 to be anywhere along Z3. And it's better to look at X3. X3 has to be perpendicular to Z2. Z2 is downward, so X2 can literally, in this case, be any vector. as long as it's horizontal or it is perpendicular to the plane. Okay, they would both work. And what we typically do, we try to do minimal rotations. If I can keep the same orientation going from 2 to 3, it reduces the number of those four parameters, A, D, alpha, and theta. Instead of one of them being a constant number or two of them being constant number, a couple of them can be zero. So we try to really reduce the number of non-zero parameters in those four important variables. So if I can choose my x3 to be the same as x2, z2 to be the same as z3, and of course y3 to be the same as y2, that means no rotation. So it makes my rotation matrix for these two to be identity matrix, which is the most convenient case. Okay, so now I'm done with the first four frames. Now I'm down to the end effector. And here is the part that you have to follow the rules of whatever method you want. If it's a gripper, you might go with that SNA method I told you. But keep in mind that your SNA method, the approach, if you make it Z, if you make your approach direction Z, so you make this one, for example, Z4, now which direction can you choose as to be X4? X4 has to be perpendicular to Z3, right? And perpendicular to Z3 here means it has to be out of the plane or again horizontal. So here you see I'm doing my Z to be approach, not my X to be approach. Can I choose my approach to be X? No. In this case, can I say this is my X4? No. Why? Because it does not intersect Z3. So you see, in this case, again, I have to go back and say, no, my approach is what? My approach is Z4, not X4. So that's why in general, I do not like that SNA approach, because depending on the situation and depending on the orientation of this end effector, the gripper, the setup of the axis could easily violate these two basic assumptions of the DH. So I personally prefer to not go with that and just set up the X, Y, and Z of the last frame to follow the same thing that I did for the rest of the axes. So what I want here is basically my new X is intersecting the old Z. And if I select this to be my new X, it's not going to intersect and perpendicular to the old Z. So my new X has to be either like this, or it has to be like this, one of these. It's up to me to decide. Okay, it is absolutely up to me to decide. And so if I go with this case, so say this is X4 and this is Z4 and then this is Y4, that gives me the simplest scenario possible, because again from 3 to frame 4 there is no rotation, so that makes it very convenient. Or I might say, well, no, this is what I do. I would call this one X4, perpendicular to Z3, yes. Does it intersect it? Yes, because if you continue Z3 and if you continue X4, they would intersect at this point. And then what? And then I choose the actuation axis of, but this is not a joint, this is the end effector. If I say I choose the actuation joint on the end effector to be Z, so I say this is Z4, then based on that X4 and that Y4, I have to, if you see here, this is going to be my Y4. right? Downward. Sure, I can do that, but the problem is now if I want to align x3, y3, z3 with x4, y4, z4, I need some twist angles. I need a couple of angles. I need theta and I need alpha, both of them non-zero to align them. Okay, and it does not give me really any advantage. So in this case, instead of choosing this one to be x4, I would choose what? I would choose this guy to be x4. That makes life easy, and I choose z4 to be this one. And accordingly, this is going to be y4. And there is no rotation whatsoever, which makes my life easier. I don't need any theta, I don't need any alpha. You see? Any extra theta. I mean, there is a theta 4, but you have to add an extra angle to that theta to align them. I'll show you. So this is going to be my origin 4. So for end effector, since we don't consider the actuation of that to be one of the actuations of the robot, we are not really forced to choose Z to be the actuation of the end effector. Okay, for the last frame, I would rather stick to what? To the two assumptions of the DH. Good. So this is your 2D planar. This is your Scara. And now that we have these, it is time to look at something new, which is called the DH table. What is DH table? DH table means I will find these 4 parameters between each 2 consecutive frames, and I will write them down as a table. What does that mean? It means here, well, I have 2 sets of subsequent frames going from 0 to 1 and going from 1 to 2. So what I will do is this. I will form a table, okay, and then here I would say this is if you remember, the order of them were theta, D, A, and alpha. So this is for frame 0 to 1, okay, or for link 1 or joint 1, and this is for joint 2, which means this is basically between link 0 and 1, links 0 and 1, and this is what? Links 1 and 2. Okay, now let's see what we should do, how we can fill out this table. So first I'm going to go from frame 0 to frame 1. What are the parameters? The first thing I need is a rotation about the old Z, which is this Z. I rotate about the old Z to align the x-axis. In other words, align the old x with the new x. Well, how do I align them? It's clear. I have to rotate about z0 with this angle theta 1 that you see to align what? x0 to x1. So clearly it is going to be what? The variable theta 1, the rotation of the first joint. Good. Then, do I need to move now along the old Z, to go from origin 0 to origin 1? If I want to go from origin 0 to origin 1, do I need to move along the old Z, which is basically out of the plane? No. Going from O0 to O1 does not need any motion out of the plane. Z0 is out of the plane. So I do not need to have any what? Any offset. So the offset here is what? 0. Then what? Then A. A means what? Means now if you want to go from origin 0 to origin 1, now you move along the new x. Well, should I move along this new x here? Should I move along this direction? to go from origin 1 to origin 0 to origin 1? Well, absolutely. I need to go as much as the length of this member, which I might call it A1. So A1 is the length of this first link. Yes. So I need to move that much. So I would call it A1. And now that I'm there, I have already aligned my x-axis through theta 1. I'm gone from this point to this point. Do I also need to rotate about the new x to align the old z with the new z? This is old z, this is new z. Are they aligned, or do I need to rotate about x1 to align them? You see, they are already aligned. They are both out of the plane toward me. They are already aligned, so no twist is needed. So the twist angle I need is 0. Clear? So that's how I go from frame 0 to frame 1. And then, fine, now let's go what? Now let's do the same thing and go from frame 1 to frame 2. How do I do that? Again, first, do I need to rotate about the old z, which in this case is z1? Do I rotate about z1 to align the old x, which is x1, with the new x, which is x2? Well, clearly you see the angle I need to rotate, correct? The angle I need to rotate here is definitely what? Angle theta 2 to align them. So yes. And it is positive. About z1 theta 2 is what? Positive. So it is going to be positive theta 1 and theta 2. Then do I need to, when I go from origin 1 to origin 2, do I need to travel along the old z, which is out of the plane? Well, absolutely not. So this is 0. Good. Do I need to travel along the new x, x2, to go from O1 to O2? Sure, that's the length of this member A2. Yes, I have to do that. How much? As much as A2. And it is clearly in the positive direction of x2, so this is also going to be positive A2. And now that I'm here at this O2, the x's are aligned, the origins are aligned. Do I need to align z's as well by rotating about x2? No, they are both z1 and z2 out of the plane in the same direction. No alignment is needed, so the twist angle is what? Also 0. So this guy here that I formed, this one is what we call the DH table. It tells me the parameters I need to go from one frame to the other. Okay, it's very important. And how do I use it? Fine, I said this. Now it is time for me to go and use this important formula that you can see here for the total what? For the total transformation that I need. So if you look here, the form of the general AI matrix is something like this, right? So now with those numbers in the table, let's form this A matrix for each one of my transformations, for each one of my joints, and see what I get. So if I plug in the numbers in the first row, these guys, if I use these ones, it will give me matrix A1, which is going to be what? We're going to plug in C of theta, so it is going to be C of theta 1, or you can call it C1 if you want. Then what? We have what? Negative of S of theta 1, C of alpha. How much is alpha? Alpha is 0. Cosine of 0 is 1. So that's 1. The sine of alpha is 0. This is 0. This is 1. This is 0. Okay, and also D is 0. So this guy is 0. A is A1. So what would you get? You will get negative sine of theta 1. The next one is going to be 0. Then you have a Since the sine of alpha is 0, you will get another 0 here. You will get a 1. You will get a 0 and a 0. 3 zeros down here. A 1, a 0 here. This is going to be A1 C of theta 1. This is going to be A1 S of theta 1. And these guys are going to be S of theta 1 and C of theta 1. So this is what you will get. Now, does that make sense? Absolutely. Why? Because if you look at the rotation matrix part of it, what is this? This is a rotation about the z-axis with angle theta 1. And of course it is. Because if I want to go from frame 0 to frame 1, I definitely need to rotate about z-axis with angle what? Theta 1. So it absolutely makes sense. And if you want, I can call it rotation about z0. What about this? How do I go from the origin of 0 to origin of 1? It says these are the displacements that you need. No displacement along z0. How much displacement along x0 and y0? A1 cosine theta 1, A1 sine theta 1. And of course it is, correct? If you look at this displacement, this one here, that's A1 and theta 1. So this is A1 times cosine of theta 1. And this vertical displacement is clearly what? A1 sine of theta 1. So I need to move that much along x0, along y0, and no displacement along z0, and that is exactly what you see. This is d of 1 with respect to 0. Right? And these are the displacements, as I said again. This is the displacement along x0, this is the displacement along y0, this is the displacement along z0, this is the rotation about z0. This guy will take me from frame what? Frame 0 to 1, or if I want to project the point back from 1 to 0. So that is my A1. You see, it's very clear, the meaning of it. And now, what about frame 2? For frame 2, I'm going to use the values in the second row. And if you use the second row, it gives you something exactly similar. Well, this one is going to be C of theta 2. Negative S of theta 2, 0, then you will get A2 C of theta 2, A2 sine of theta 2, 0, 1, 0, 0, 0, sine of theta 2, cosine of theta 2, 0, 1, 0, 0, which again completely makes sense because again this is a rotation, and this is rotation about what axis? Remember, you are going from 1 to 2, so this is a rotation about z1 with angle theta 2, and this is a displacement of which with respect to which? Origin 2 with origin 1. So this displacement A cosine theta 2, A sine theta 2, and 0 are along which axes? Well, you tell me. They are along the axis of the old frame, which in this case is 1. So they are this distance. This one, which is A2 cosine theta 2, and it's this one, A2 sine theta 2. Right? So they are along x1, y1, and z1, because your reference here is 2 with respect to 1. So this is motion along x1, this is motion along y1, this is motion along z1. Good? So now that I got a1 and a2, the homogeneous for 1 and 2, now it says what? If you remember, it said that if I multiply them together, pre-multiply, it will give me the one that takes me from 0 to 2, or 2 to 0. So in this case, if I want h of 2 with respect to 0, it is h of 2 with respect to 1 with respect to 0 times 2 with respect to 1. And this h of 1 with respect to 0, that's the same as a1, and this guy is the same as what? a2. So all I need is to multiply these two matrices together. If you do it using MATLAB symbolic or you do it manually, what will you get? Well, what you will get is going to be, if you look at the terms, it is going to be C of theta 1, C of theta 2, correct? And then plus sine, or no, minus sine of theta 1 times sine of theta 2. The same element you will get here in 2. What will you get here and here? Here you will get sine of theta 1 cosine of theta 2 plus cosine of theta 1 sine of theta 2. And here you get negative of that. Then you will get a 0, and 1. And 0, 0, 0, 1. And finally, these elements, this is going to be A1 times C of theta 1 plus A2 times C theta 1 C theta 2 minus S theta 1 S theta 2. This is going to be A1 sine theta 1 plus A2 times sine theta 1 cosine theta 2 plus cosine theta 1 sine theta 2. Then you will get a 0 and a 1. So this is what you will get as the overall H matrix. Will take you from the end effector frame 2 to back to frame 0 to the base, or depending on how you describe it. So this here is clearly what? Your rotation matrix. This is rotation matrix of frame 2 with respect to 0, and this guy here is what? This is origin of frame 2 in 0. Now, if you look at these trigonometry terms, you know that cosine of theta 1, cosine theta 2 minus sine 1, sine 2, this guy here is cosine of theta 1 plus theta 2. Okay? Which, by the way, we might show it with the notation C12. So remember, C1, we said that's what? That is cosine of theta 1, if we want to use simple notations, right? Or sine 1, we said this is what? S1 is sine of theta 1, for example. Now here, if you see from this point on, C12, that means cosine of theta 1 plus theta 2, and S12 can be sine of theta 1 plus theta 2. So here I'm trying to show you some notations, okay? So instead of that, I can say this is going to be what? This is C12. This is negative sine of 1 plus 2. this is sine of 1 plus 2, and this is cosine of 1 plus 2. So now what kind of format is it? If you look at it, definitely it's a Z matrix. So this is a rotation Z matrix. And what is the angle? Well, the angle is theta 1 plus theta 2. Is that right? Absolutely. Because what I did is, if I want to go from the orientation of frame 0 to frame 2, all I need is 2 rotations. One time do it at theta 1 of Z, and then what? At theta 2 of Z. Since they are in the same direction, I can simply what? Add them together. So by a simple rotation about Z, and here I mean Z naught axis, with angle theta 1 plus 2, I can align my my frame 0 to frame 2. That's all I need. If you look at them, they share the same Z. Their x's and y's are rotated by a simple Z of theta 1 plus theta 2. That's all it is. Okay. And what about D to 0? It says it's A1 sine theta 1 and plus A2 cosine of 1, 2. A1 sine theta 1 plus A2 what? Sine 1, 2. Is that correct? Absolutely. Again, if you look at the geometry of it, so I'm looking into the location of this point with respect to this point, where this is A1, this is A2, this angle is theta 1, and this angle here is theta 2. Well, what is the total displacement in x and y? Well, there is no displacement along z naught to go from the first point to the last point. So that's clear why this element is 0 here. But if you look at this x and y, so remember this is your x naught direction, and this is your y naught direction. So how many x naught, how many y naughts do I need to go from the first point to the last point? Well, clearly here, this displacement from here to here is A1 cosine of theta 1. How much is this one from here to here? If I add that, I'm done. Well, for that, I need A2 and I need this angle. I need this angle in blue, which is what? It is theta 1 plus theta 2. So I can say A2 times cosine of 1 plus 2, which I show as C12, that is this next delta x. And similarly, if I look at the y's, so here I have this one, which is A1 sine of theta 1, and then I have this one, which is clearly what? A2 times sine of 1 plus 2, which I show it as S1, 2. So I add these two, that's my delta y. I add these two, that's my delta x. And this is exactly what you see in these components. Right? So you see, it absolutely makes sense how I go from my very first point to what? The very last point here. Good. So this is the overall procedure for forward kinematics. First, set up the axis. The axes, all of them from frame 0 to frame n. Form the what we call the DH table based on what you see between the frames is happening, and the definitions of A, D, theta, and alpha. Form the table, then use each row of the table and form one of the A matrices, and then multiply them from the first one to the last one to get the overall what? H that takes you from the base to the end effector. And so now you have the rotation of the end effector with respect to base and the position of the end effector with respect to base. You clearly see that this guy here is a function of what? Theta 1 plus theta 2, and this rotation matrix is also what? A function of theta 1 and theta 2. So that's it. That's all that we needed. We are done. Right? So this is a function of theta 1 and theta 2, and that is a function of theta 1 and theta So that's the overall procedure. Now I'll go through the Scara example as well for you. And we'll try to form the DH table here. And then form all of the A matrices, multiply them together, get the total thing, and see if that makes any sense in here. Okay? So what do we need? So as I said, we need to form the DH table, right? So let's go ahead and see if this guy has a table for me. Yes, let me draw a nicer table. And what I need is 5 columns and I guess 5 rows. So that's my DH table. And I should be able to make this guy probably a little bit bigger as well, hopefully. No? That's okay. So this is 1, 2, 3, and 4. And then here you have theta I, and then you have di, and then you have ai, and then you have alpha I. Okay, so now that I got these, let's go ahead and based on the frames that I set, see if I can find these parameters. First row, I go from frame x0, y0, z0 to frame x1, y1, and z1. What do I need? First, do I need to rotate about the old z to align the x's? Do I? Well, you know that I do, because the first rotation here is happening about what? It is happening about the z-axis. So the way it is drawn right now, this is not the deformed version of the robot, okay? It's not. It's just assuming that here the first angle theta 1 is 0. In general, when this robot acts, if you look at this guy from the top, so this is your frame 0, then it starts rotating. This is going to be your second rotary joint. Okay, so then if you look at it from the top, as I said, this is your x0. Y0 is like this. Z0 is out of the plane toward you, which if I use this symbol to say out of the plane toward you, then frame 1 is basically, again, Z1 is out of the plane toward you, but now your X1, which is along the member, is going to be like this. And this is going to be your Y1. And as I said, Z1 is out of the plane toward you, so it's like that. So definitely, if I want to align X0 and X1, I have to rotate for what? For angle theta 1. So yes, there is a theta 1, but you probably cannot see it from this front view. But if you look at the top view, you absolutely see theta 1. So yes, there is a theta 1 involved, and that is clearly about the positive Z0 direction. So that's positive theta 1. That's good. Then do I need, when I go from origin 0 to origin 1, do I need to move out of the plane, correct? Do I need to move along this Z0, go up to go to this point? Absolutely not. So there is no D involved. Good. Now, do I need to move along the new X with the distance of A1 to go from this point to this point? Sure, I need to move this distance from here to here, and I can call this guy what? A1. So yes, it is A1. And you can see that A1 here, that's this distance. That's this link, A1. Okay, now that I got A1, do I need to spin about the new X to align the old Z and the new Z? No, they are already aligned, so there is no twisting required. That's it. Right? Now let's go from frame 1 to frame 2 and form the second row. Again, we go according to the order. And I can draw this again a little bit nicely for you. So from the top view, so that you see that I need a second rotation. So now what do I need? Let me see if I can draw the links with some other color. So now this is my second thing, and this is that prismatic joints that I have. Correct. So now I have my second rotation theta 2. And if I draw the axis here, my x2 is along the second link, so it is like this. My y2 is opposite of that, so it is going to be like that. And my z2 is in the plane, so I have to use a symbol like this. Cross. You know, a cross means in the board. So this is my x2, y2, z2. So now, first thing first, do I need to rotate about the old z to align the old x with the new x? Do I? Yes. Not in that front view you see it, but in this top view you can easily see that. Do I need to rotate about the z1 to align x1 with x2? Sure, I need the angle positive theta to make it happen. You see clearly they are not aligned. So yes, this is going to be positive theta 2. Do I need to move in the direction of z1 to go from origin 1 to origin 2? No, they are on the same horizontal level. I don't need to go up and down, so no offset. Do I need to move along the new x, x2, to go from this origin to this? Sure, that's the length of this member A2, correct? So if this is A1, this is what? A2, which you can also show it here. Right, that's this distance. So yes, it is A2. Do I need a twist? Twist for what? For aligning the x's, for aligning the z's, I'm sorry. Do I need to rotate about x2 to align z1 and z2? In this case, z1 and z2 are not aligned. They are parallel, but there is a 180-degree rotation. Yes, so I need a twist now. How do I rotate about x2 to bring z1 to match z2? Well, it can be either direction, either this way or the other way, 180 degrees. So it can be plus pi or minus pi. It is up to you. And the result is not going to be any different. Plus pi and minus I, they have the same sign and cosine. So yes, I need plus pi, 180 degrees. I need to make a rotation about this x2 so that z1 comes and aligns with z2. Absolutely. You can see that here if I draw them all on the top of each other. This is x2, this is z1, and this is z2. Clearly I need this 180 degrees rotation to make it happen, but I can go backwards and say negative 180. But again, as I said, there is no difference between them. So yes, I need a twist here because the z's are not aligned. Good. Now, how do I go from frame 2 to frame 3? How do I do that? First, do I need a rotation to align the x's? In this case, I don't. Because if I look from the top, x3 is right below x2. So if I had a way to draw it, x3 would be right below x2. And y3 will also be right below y2. And z3 is also on the top of z2. They are both, in this view, perpendicular to the plane inward. You see clearly they are both in downward in this view. So absolutely there is no rotation whatsoever if you want to go from frame 2 to frame 3. So there is no rotation either about the old z or about the new x. So both of my angles here are 0. When there is no rotation, both of the angles have to be 0. What about the D and A? Do I move from O2 to O3? Do I need to move along the old Z? Absolutely. It is equal to this distance that your prismatic joint travels, correct? You know that your prismatic joint travels a distance of D3. That's one of the variable numbers, D3, to go from O2 to O3. So yes, the answer is yes. This is called D number 3. When you get there, do you also need to move along X3 to set the origins on the top of each other? No. So I do not need anything here. Good? So you see how I set up the third row. And now that you got that one, let's go to the last one. How do I go from 3 to 4? Well, clearly, again, you see 3 and 4 are perfectly aligned, all of the axes. When the axes are all set, means there is no rotation needed whatsoever. Do I need to go from Z3 to O3 to O4? Do I need to move along Z3? Yes, that's this offset from here to here. That is this offset. Okay, and this offset, you can call it some constant D4. So you say, yes, I need some D4. And do you need to move along the direction of X4 to make it happen? No, Z. Now, is that all correct? The answer is no, it's not. There is one thing we missed. What was it? Yes, you are right, theta 4. Again, yes, if I look in this front view, it can be misleading. Because in this front view, I do not see the rotation what? The rotation theta 4. I'm not going to see that. So it makes this guy for me 0 while it is not. So if I want to see theta 4, I have to come and look at it from the top. That can easily throw you off, okay? So if you want to determine the parameters, make sure you look at your manipulator at least in 2 different directions. So if you look now, when the angle theta 4 is in effect, since it is about positive Z4, if I call it positive Z4, so the rotation of that is going to be actually backwards. So it's not going to be like this. It is actually going to be like that. Because Z4 is, Z3 is downward. So what does that mean? It means if I want to show the orientation of frame 4, how does it look like? Well, let me use a different color here. So it is going to look like this. No, I want black. And Z is still on the top of the rest. So Z4 is the top of the Z3, Z4, Z3 and 2. But this is going to be your X4 and this is going to be your Y4. And to go from X3 to X4, you need a rotation backwards with angle what? Theta 4. Do you see that? Which is positive of the rotation about Z3. Okay, but you go backwards. So yes, there is an alignment needed between X3 and X4, and the angle is what? Theta 4, which is about the positive direction of Z3. So yes, this here is not really 0. This is actually what? Positive theta number 4, and that can easily throw you off. Okay, so please pay attention to that. Good. So now I got my table right. And if you look at this table or the previous table that we had, remember I told you one important thing and I want to re-emphasize that. If you look in each row of the table, only one of these four parameters is variable. What is it here? If you look between A1 and theta 1, which one is variable? Theta 1. Between A2 and theta 2 is theta 2. A1 and A2 are the geometry, the length of the links. They are fixed. Only theta 1 and 2 are the only variables. If you look here now, what about these? In the first row, it's only theta 1 that is variable. In the second row, it's only theta 2. A1 and A2 come from geometry. Pi is a fixed twist. What about the third row? Is D3, the amount of displacement of the prismatic joint. What about here? It's only theta 4. D4 is, again, a part of the geometry. It's an offset. So you see, in each row, there is only one parameter variable. And to distinguish that parameter from the rest of the parameters, what I would like to do is put an asterisk next to the variable and not put asterisk next to the constant parameters. So if you see I put an asterisk next to some parameters, it means those are the variable parameters. The rest of them are going to be constants from the geometry. Okay, so now this is going to be your good DH table. Right? So now that I got my DH table, it is time to go and form my what? My A matrices. So again, I go back to this thing that I had. Let's see if I can find it here. I go back again to this definition of the A matrices, and then I go row by row, apply them, and I will get my A matrices. Okay, so first I go over the first row, which are these guys, plug them in, and I will get my A1 matrix, which if you do here, it is going to be C1 negative S1 0 A1 C1, then S1 C1 0 A1 S1, and then 0 0 1 0 0 0 0 1. So that comes from the first row. Then we go and look at the second row. So we pick the parameters of the second row here. That will give me my A2 matrix, which look a little bit different, maybe or maybe not. Yes, it is. Why? Because that twist angle of pi. Let me do that. So it is going to be C2 S2 0 S2 negative C2 0 0 0 negative 1 0 0 0 1 A2 C2 A2 S2 and 0. Okay, and I'll discuss them one by one. Then we go to A3, right? So we pick on the third row values, these guys. It's going to be very simple. There is no rotation involved. It is just a translation of Z. With D3. Okay. So this is going to be my A3 matrix. And finally, I'm going to pick on the numbers in the fourth row, and that should give me my fourth matrix A. Which if I evaluate it, it is going to be C4, negative S4, then 0, 0, then S4, C4, 0, 0, 0, 0, 1, D4, and then 0, 0, 0, 1. Okay, so these are my four homogeneous transformation matrices. Do they make sense? Absolutely. Let me explain them to you. So clearly, if you look at the first one, the rotation matrix which describes the rotation of 1 with respect to 0 is a rotation of what? It is a rotation of z and angle theta 1. And absolutely it is, you know that we are rotating about frame z0 with angle theta 1 to make it happen. So that makes complete sense. And the displacement is, of course, A1, C1 and A1, S1, which you can clearly see here in this picture, right? This is A1, that is theta 1, so these displacements here and this one. This is A1, C1, and this is A1, S1. Very clear. Yes, so there is no ambiguity here. Now, when we go from frame 1 to frame 2, the rotation looks like a Z rotation, except that it has some negatives in it. So this is rotation of 2 with respect to 1. It looks like a rotation Z with angle theta 2, except, as I said, first of all, this has to be negative sign, not this one. Negative cosine, so this negative should go up there, and this should be positive 1. So why is it like that? That's all because of that spin. The twist, pi. The pi twist that you see here, it's just because of that. Now, does that make any sense? Well, let's take a look here. What's the meaning of, let's say, this third column? What is this? This means how I can write Z2 in terms of what? X1, Y1, and Z1. So it is like Z2 dot X1, Z2 dot Y1, and Z2 dot Z1, right? If you remember, that was the meaning of each column of a rotation matrix. So it means if I want to write Z2 along the axis of X1, Y1, Z1, Z2 is aligned with negative Z1 and nothing along X1 and Y1. Now, is that true? Absolutely. If you look, Z2 is the same as Z1 but negative, and it has no component along X1 and Y1 in whatever direction that you use, front, top, whatever. You see that Z1 and Z2 and Z1 are the same line, just negative direction. Z2 has nothing along X1 and Y1. So you see that completely makes sense. But let's see what's going on with this second column here. Does this one make sense? Well, what does that mean? This means Y2 return in terms of X1, Y1, and Z1. It says Y2 has nothing along Z1, but it has sine theta 2 and negative cosine theta 2 along X1 and Y1. Does that make sense? Well, let's take a look at this top picture. So I'm trying to look at Y2, this axis. Clearly, you see it has nothing along Z1 because Z1 is out of the plane here, Y2 is in the plane. So of course there is no component. I'm trying to write that in terms of this Y1 and this x1. And I assume, based on this angle theta 2, it is rather clear why you have those components, correct? Yes, if I draw it somewhere outside for you, just these guys. So this is x1, this is y1. And then you have a rotation of theta 2 to make x2. So x2 is like this, and this is y2. And remember, this angle is theta 2. So this angle is 90 degrees minus theta 2. Right? So if I decompose it along y, it is going to be sine of 90 degrees, what? Minus theta 2, which is cosine theta 2. But clearly you see this in the negative direction of y1. So, right? So this component here, that is going to be negative of sine of 90 degrees minus theta 2, which is equal to negative cosine theta 2. And this component, which is along x1, this guy, this is going to be cosine of 90 degrees minus theta 2, which is sine theta 2. So now clearly you see where sine theta 2 and negative cosine theta 2 are coming from. And similarly, if I decompose x2 along the x1 and y1, you clearly see that x2 has a sine component along y1 and then a cosine component along x1, which you can see here. Cosine along x1, sine along y1, nothing along z1 because x2 is perpendicular to z1. So you see the meaning of each column is clear, and clearly you cannot call this a simple z rotation because it doesn't match the format. And then again, the displacements from origin 1 to origin 2 are A2, C2, A2, S2. And if you go take a look, you clearly see that again. Right? This is A2, that's theta 2. So what you are doing, you are projecting this red vector A2 along this axis and along this axis. So that is one, and the other one is like this. Right? So clearly this one is A2 cosine theta 2, and this one from here to here is A2 sine of theta 2. And that is what you saw in that displacement vector. Right? So that's clear as well. Then we go to the third one. The third one, there is no rotation whatsoever. It's an identity matrix. Of course it is, because if you look at 2 and 3, 3 and, 2 and 3, that's right. You look at 2 and 3, you see they are exactly the same direction in all different views. There is no rotation whatsoever, so it has to be an identity matrix. And the displacement, all it is a d3 units along what? Along the z2 axis. That's only this guy, which is along z2, and that should be it, because if you look here, I'm moving d3 units in the direction of z2 to go from origin 2 to origin 3, so that works completely fine. Finally, if you look at the last one, again, this rotation matrix here, which is rotation of 4 with respect to 3, is clearly a rotation z. Which z? z3 in this case, and the angle is theta 4. And the displacement is also the 4 units, which is also along z3. And you clearly can see that as well here, that I have a rotation of theta 4 to align them about z, and I have to also move the 4 units allowing Z3 to go from O3 to O4. So each one of these A matrices makes absolutely reasonable sense. And now I say H of 4 with respect to 0 is simply A1 times A2 times A3 times A4. So what I need is to multiply these 4 matrices in MATLAB using the symbolic toolbox. And if you do that, then you will get some big thing, which is C12, C4 plus S12, S4 negative C12, S4 plus S12, C4 S12, C4 minus C12, S4 negative S12, S4 and negative C12, C4 0, 0 0, 0, negative 1 0, 0, 0 A1, C1 plus A2, C12 A1, S1 plus A2, S12 negative D3, negative D4 and 1. Okay, so this is going to be your ultimate answer, which if you look at it, this is your rotation matrix. This is rotation matrix of the end effector with respect to base, and this is the displacement of the end effector, the position of the end effector with respect to base. Clearly, you see they are functions of theta 1, theta 2, and in this case, just theta 4. There is no D3 in it. And here, this is a function of theta 1, theta 2, and D3. There is no theta 4 in it. So it doesn't mean that the rotation matrix in general, the rotation matrix and the position of the end effector with respect to base, they have to be the function of all of the joint variables. No. They are sometimes function of some of them and not some others. Okay? Now, again, do they make sense? Absolutely. If you look here, for example, look at this component. How do I go from the base origin to the end effector origin? If you look here, I need to move along this Z naught, a distance of negative 3, and then what? A distance of negative 4, right? Or D3 and D4 in the direction of negative Z naught. That's why these two come into play. Right? If you look at this matrix, this is very similar again to a rotation Z matrix, except for this negative 1. And these guys, you can even go according to trigonometry and look at them. If you look, this is the cosine of theta 1 plus 2, which is the first guy, minus 4. This is what? This is the sine of theta 1 plus 2 minus 4. This is, well, let me make sure. That's right. This is also the sine of theta 1 plus theta 2 minus theta 4. And this is negative of cosine of theta 1 plus 2 minus 4. Again, it's not a perfect Z matrix. The orders of sine and cosine is a little bit different. This is -1, and you know all of that is happening again because of the twist. But here you clearly see something matters, and that is θ1 plus 2 minus 4. Why does it matter? Because if you look, all of these rotations 1, 2, and 4 are happening about the z-axis. The first two are in the positive z-naught. The last one, this θ4, is about negative z-naught. So the total rotation z is what? θ1 plus 2 because they were positive, and then minus 4 because it was negative z-naught. So that's why you see θ1 plus 2 minus 4. And these are again very clear. Remember, these two are the exact same thing we had for the 2DOF, correct? If you look at the 2DOF planar arm, you see they are the exact same thing here. Why? Because basically a Scara robot is what? It is a 2 degree of freedom arm where you add 2 extra degrees of freedom to it. If you see here, this portion of the robot is a 2DOF planar arm. And then you add 2 more degrees of freedom to it, a prismatic and a rotary, and that makes it a Scara. So the first half of the Scara is simply a 2D planar arm. That's why some of the stuff you see here are similar to what you see over here. Okay? So this video is already at 2 hours, 10 minutes, so I'm gonna stop it here. I have more examples to work on, and that is the cylindrical manipulator, that is the spherical wrist, and then combining them together to make it a 6DOF robot. We will work through those, but in my second video. And then I will show you the forward kinematics using vector addition method, which is a separate method. Okay, so let's stop this video here, and I will see you in my next video. Thank you.